Number 38. Statistics from Cornell's Northeast Regional Climate Center indicate that Ithaca, New York gets an average of 35.4 inches of rain each year. 35.4 is your mean, with a standard deviation of 4.2. During what percentage of years does Ithaca get more than 40 inches of rain? That's A. B says less than how much rain falls in the driest 20% of all years. So the driest 20%. If I look at a normal model, that's going to be this lower 20%, right? Dry would be small amounts of rain, right? Wets would be, a wettest 20% would be the more rain. So we're looking at the lower 20%. That's inverse norm, 0.2. If you're using left, center, right, you're going to make it left, right? Because this is left, center, right, if you're using inverse norm. If I want the driest 20%, it's going to have the least amount of rain, right? So smaller numbers. So inverse norm 0.2 is negative 0.8416. And then we plug it into my z-score formula, x minus mu over sigma. So negative 0.8416 equals x minus 35.4 over 4.2. We're talking about a single year, how much rain falls in the driest of that years. So we'll multiply by 4.2 and then add 35.4. So I get x equals 31.87. So the driest 20% of years get 31.87 inches of rain or less, okay, which is totally foreign to us. We'd be like miserable. When will this rain stop? We get a week of rain and we're complaining. So then, how is it different when it asks about a 4-year average? How does my calculation change when it asks about a 4-year average? Jacob? I have to use the mean. Yes. My mean is still 35.4, but what's my new standard deviation if I'm talking about a 4-year average? Yeah, sigma over square root 4. So 4.2 over square root 4, which would be 2.1. Once you have a sample size, you have to use sigma over square root n for the standard deviation. Ava?
So like there's just more samples and there's just like the initial question, it wouldn't matter. But as soon as like anything comes into play, like time or like amount of people.
Yes. As soon as you have a sample size, and now we're talking about not just the how much rain you get in 1 year, but we're talking about averaging 4 years together. Now we're looking more at the sampling distribution, and we need to use the sigma over square root n. So if we have a sample size, if we have an n, we need to use the sigma over square root n. No, because our units that we're talking about are inches per year. So we're talking about how much rain they're getting in a year, so that's 4 years is our sample. Layla? Yes, we should always do the conditions. Now, the C is where you would check the conditions, right? It says, describe the sampling model distribution for the mean. If you're describing the model, you have to make sure the conditions are met so that you can use the model. Now, for 4 years, does that meet our central limit theorem? No, 4 years does not. But it says assume a normal model applies. Okay, as soon as it says assume a normal model applies, that means our condition is checked for the central limit theorem. Yeah. No, our conditions are, our conditions are still randomness, right? If we're picking 4 random years, or are those 4 years representative? Is it less than 10% of all years? So then that's your central limit theorem. If you are pulling from a population that's not normal, then you need to have a sample size at least 25 so that the sampling distribution will be normal. Because it tells us a normal model applies, it's telling us that we can check off that condition, okay? Even if our sample size isn't large enough, because when this population is normal and we're pulling from a normal population, then it makes sense that the sampling distribution would also be normal. But it's when the sampling distribution is coming from a skewed population that we need the sample size to be really large. Over 25 is our really large number. Okay. Okay, so 40C. Okay, 49C. A waiter believes the distribution of his tips has a model that's slightly skewed to the right with a mean of 9.6 and a standard deviation of 5.4. A says, explain why you can't determine the probability that any given party will tip him at least $20. Why can't we do that? Why can't we use the z-score and find that? Why can't we use the z-score to find the probability that any given party will tip him at least $20? Well, one table is not a large enough sample because the distribution is skewed. You can't use the normal model. When he believes the distribution is skewed to the right, we can't use a normal model calculation on a skewed distribution. Okay? So because he says right here, it says slightly skewed to the right, 2 standard deviations of the mean is 0, right? You can't tip less than 0. So you can't be 2 standard deviations from the mean. You can't be 3 standard deviations less than the mean. So the data is skewed, and therefore you do that calculation. Can we estimate the probability that the next 4 parties will tip an average of at least $15? No, 4 isn't large enough for the central limit theorem to apply, right? And even, is it likely that 10 parties today will tip an average of at least $15? Can we find that calculation? No. Is it likely? That's how many standard deviations from the mean. Like, 1 standard deviation from the mean is $15, right? 14, no, it's 15 even. Is it likely that an average of 10 tables is going to be a whole standard deviation from the mean? No. Okay. If you could apply the normal model, your standard deviation would be much smaller. 10 is still not large enough to use the central limit theorem, though. We can make an estimate and say probably not, because the more tables you average, the less they're going to vary from the mean, right? The less that average is going to vary from the mean, so it's not likely. What was my 49 and 51? So 51 says, more tips. The waiter in exercise 49 usually waits on about 40 parties over the weekend. Now can we apply the central limit theorem? Yes. Okay, so we can say for our conditions, okay, I'm telling you right now, you have to check conditions on both questions on the quiz or you're going to miss 8 points. You're going to miss 8 out of the 20 points if you don't check conditions on each question. The sample, is it random? Does he get to randomly choose his tables that he waits on? No. But is it probably representative? They're not like, and the tables that he gets in a night are not necessarily randomly assigned, but they take turns, right? So it's probably very representative. They don't send the first 10 people to one waiter. They try to disperse it over all the waiters. So the sample is representative. And don't say it's representative when it's actually a random sample. If it says a random sample of this, you need to say the sample is random, not representative. Representative is our default when we can't say it's a random sample. So the sample is representative. 40 is less than 10% of all his tables. We're not talking about all his tables that night, but all the tables he will wait on as long as he works for more than one day, right? So it's less than 10% of all his potential tables. And then 40 is large enough to apply the central limit theorem. And so estimate the probability that he will earn at least $500 in tips. So if it's 40 tables, how is he going to earn $500? What is he going to have to average? $12.50, 500 divided by 40. He's going to need to average $12.50 per table to make at least $500. Okay, so the mean is still $9.60. His standard deviation is 5.4 divided by the square root of 40. And we have to say, since conditions are met, a normal model is appropriate. You're going to get 1 point for the random condition, 1 point for 10%, 1 point for central limit theorem or NP and NQ, depending on whether it's a proportion or a mean. It'll have one proportion and one mean problem, and 1 point for saying this sentence. Those are easy 4 points. The rest is the calculation. You'll get points for calculating the standard deviation correctly. You'll get points for calculating the z-score correctly, right? And then points for calculating the probability correctly. So 5.4 divided by the square root of 40. So the standard deviation of the mean here is 0.0854. And my z-score calculation, what mean does he need to achieve for this goal of $500? 12.5 minus the mean, 9.6, divided by the standard deviation, 0.854. Oops. I put my decimal in the wrong spot. I got 3.4. Yep, 3.4. Is it likely? No, but it doesn't say is it likely. It said estimate the probability, right? So what do I put that into? Normal CDF. And is it negative 99 or is it positive 99? Positive, right? He needs to make at least $12.50 to make at least $500, right? So I want $12.50 or more to reach my goal of $500 in tips, right? So what's the probability that he makes at least that much? It's 3.4, 99. And that's in the second distribution menu. And we get 3.37 times 10 to the negative 4. Pay attention when the number is above 1. That means there's scientific notation. Yes, Faith.
Sorry, earlier when you were talking about if it asked how likely something was,
Mm-hmm.
and then you said that's all it's asking, so it doesn't use
So if it said, is it likely, you could stop and say, no, it's not likely because $12.50, an average of $12.50 is more than 3 standard deviations from the mean, which is not likely at all. Right? So if you're 2 to 3 standard deviations above the mean, you can say, at that point, use the z-score as a justification because more than 2 standard deviations from the mean only happens 2.5% of the time. So you wouldn't have to get the probability, right? If it's asking, you can and say, no, it's not likely because it's 0.000337. There's a really, really small chance of that happening, right? So both our probability and our z-score tell us if it's likely. Okay. So you could also say, no, it's not likely because there's only a 0.000337 chance of making an average of 1250 per table. But make sure you answer that question. If it's, is it likely, you need to answer that question in context of the problem. Don't just say, no, it's not likely. Right? You want to explain why with talking about the tips or whatever the question is asking. Okay. And then B, how much does he earn on the best 10% of such weekends? So the best 10%, that's going to be inverse norm 0.9. If I'm doing left, center, right, I could do 0.1 right, because that's the right. The best 10%, he's making the most, which is 1.282. Inverse norm 0.2 is negative. Never mind. Wait, wrong number. It's 0.1. 1.282. And it's positive, right? Because it's above the mean. The upper 10% is above the mean. That's the other thing you can make sure to think about. Whether you do inverse norm 0.9 or 0.1, you're going to get 1.282. If you do 0.1, you get this number down here, and it's a negative, right? So drawing the picture reminds me that this should be a positive because I want the upper, and it's above the mean, so it should be a positive z-score. If I want below the mean, I need the negative z-score. Remember, it's symmetrical. Do you have a question, Faith? What? Well, the whole thing adds up to 100. So if I want the upper 10%, I have to ask the calculator for the bottom 90%. Okay, remember, I'm going to always do this with the left command because some calculators don't have left, center, right. Okay. And that is x minus 9.6 over 0.854. What was it? Yeah. So we'll multiply by 0.854 and add 9.6. And it's actually x bar. It's the average. So the best 10% of weekends, he averages 10.69 per table. Then you can times that by $40. By 40 tables, he makes an average of 427.78. So, we're getting down into the really, really relevant part of this class. Talking about confidence intervals. This is chapter 19. Now, the rest of this unit, we're going to deal solely with proportions. Chapter 18, we looked at the sampling distributions for proportions and means. And this chapter and the rest of them up to 22, we're only going to focus on proportions. And then the next unit focuses on means. Okay? So a confidence interval for a proportion talks about things like how accurate is that test result? We can say it's maybe 92% accurate, but there's a margin of error with that. Who will win the midterm elections? Who will win presidential elections? Presidential elections and state elections are all estimated with a a margin of error of 3%. And you were supposed to read that article that kind of talked about what margin of error is, because for margin of error and confidence intervals, Chapter 18 dealt with, we know the population proportion. And can we make these calculations based on that? We don't usually know the proportion of people that are going to vote a certain way, right? That's why they do polls. They take samples of 1,000 people. It's almost always 1,000 people, random samples. They meet their conditions. The sample size is large enough for NP and NQ to be greater than 10. It's less than 10% of the population. The sample is random, okay, so they can use a normal model. But we take a sample of 1,000 adults that are registered to vote and try to estimate what's going to happen on election day. But we know that that's not going to be the exact percentage that happens on election day. And we know that when we take the poll next week, we're going to get a different percentage as well. So we estimate within a margin of error. And that margin of error for those types of polls are 3%. Okay? Think about your response bias project. Okay? Let's just go over here to the Chick-fil-A or Cane's. Okay? 40% of people said Chick-fil-A when you were wearing the hat. Is that going to happen every time you ask? No, you're going to get a different estimate, right? So if we're really going to estimate the population percentage that prefer Chick-fil-A over Cane's, we have a margin of error, and we can create margins of error for our samples. Okay, we know that it's going to be somewhere around 40%, but it's going to vary with some margin of error. And it's not 3% because our sample size is kind of small. Sample size of 25 for that question is not a huge sample size. But we know that it's going to vary, and that margin of error tells us how much we believe it's going to vary. So the confidence interval for a model parameter, in this case we're trying to estimate the population proportion of something. Say a 95% confidence interval is the most common confidence interval that's used. 95% of all random samples will yield intervals that capture the true parameter value. 95% of the time, the confidence interval will capture the true percentage of people that are going to vote a certain way. Will capture the true proportion of people who prefer Chick-fil-A to Raising Cane's. We estimate that margin of error, it's about 2 standard deviations, right? Our 68, 95, 99.7 rule tells us that about 95% of the data lies within 2 standard deviations of the mean. So we can estimate that by above 2 standard deviations above the mean, and 2 standard deviations below the mean. It's actually exactly 1.96 standard deviations from the mean is 95%. So a confidence interval for a poll that estimates the percentage of yes votes on a school budget to be 52% with a margin of error of 3%. So if my point estimate, 52% would be called my point estimate, the margin of error would mean we're going to add 3%. So my confidence interval is between 55 and what? 49. So based on that confidence interval, we're going to add 3% and we're going to subtract 3%. Is it possible that the vote does not pass? Doesn't get enough to pass? We need 50% to pass. So based on this confidence interval, it's possible that this school budget does not pass because we predict that somewhere between 49 and 55% are going to vote yes. So if only 49% vote yes, it fails. If 55% vote yes, it passes, right? This is where they call things too close to call. It's too close to call one way or the other. When we interpret a confidence level, okay, we start using more cookie cutter statements. We had cookie cutter statements in chapter 9 when we talked about slope and y-intercept and the r squared. Now we have confidence level and confidence intervals. In repeated sampling, 95% of constructed intervals will capture the true proportion of people who prefer Raising Cane's over Chick-fil-A. If it's a 90% confidence interval, 90% of constructed intervals will capture the true proportion of people who approve of the job the president's doing. Okay? I included this picture here. I'm going to zoom in here. Each of these bars represents a confidence interval. This line represents the true population mean or proportion. Okay? A 95% confidence interval would mean if we had 20 samples, 19 of them actually included the true proportion or true mean, and one of them missed the mark. This red one here didn't quite get to that line. So 5%, which would be 1 out of 20, didn't actually capture the true proportion. Most of the time we don't know whether it's that our sample is that one or not. That's why we only speak about being 95% confident. Because I can be 100% confident that between 0 and 100% are going to vote yes on the school budget. But that doesn't give me any information, right? I'm 100% confident between 0 and 100% of people prefer Chick-fil-A. That's not very useful, right? I want to narrow it down. If I can be 95% confident that between 30 and 45% of people prefer Chick-fil-A, then that gives me a better idea of what the population thinks, right? And I'm just using the Chick-fil-A example because it's right there and it's not political, and that's nice because, you know. Okay. So, in repeated sampling, 95% of constructed intervals will capture the true proportion of voters who approve of the president's job. They do presidential polls daily about whether or not people approve of the president's job, and they have a 3% margin of error. They ask 1,000 people. So here's our cookie cutter statement. In repeated sampling, whatever percentage it is, 90%, 95%, and 99 or 98% are the most common confidence intervals. We don't want to say I'm 75% confident. That doesn't sound very confident, right? We keep it above 90%. The most common is 95. And if you want to be 98% confident, the more confident you get, the bigger our interval is. So if I'm 95% and my margin of error is 3%, to be 98% confident, I have to get more values to be more confident. So the more confident I am, the bigger my interval is, the bigger my margin of error is, right? Because remember, I can be 100% confident that it's going to be between 0 and 100%. 99% confident, it gets a little bit smaller. The smaller my confidence level, the smaller my interval. Okay. What about our confidence interval? If we said we're talking about the school budget problem, we said, I am 95% confident that the true proportion of yes votes on the school budget is between 0.49 and 0.55. That was the interval we wrote on the previous slide. We're 95% confident that the true proportion of yes votes on the school budget is between these two numbers. I have to include context. I'm not 95% confident about my sample. My sample was 52%. It is what it is. I'm using my sample to estimate the population proportion, what's actually going to happen on the day of voting. Standard error in chapter 18, we calculated the standard deviation with the square root of PQ over N, where P was a population proportion of success and Q was a population proportion of failure. Remember, that's just 1 minus P. On your formula sheet, it doesn't use Q, it uses 1 minus P. But the reality is we very rarely know the population proportion. We know what we got in our sample and we're trying to estimate that. So when we substitute P for P hat, our sample proportion, the calculation is now called standard error. Because there's a little bit of error in there. We know that it's just based on our sample, not the actual population. The calculation is the same general idea though. Square root of P hat, Q hat over N instead of PQ over N. To calculate a confidence interval, we have what's called a Z star, or a critical value. It comes from 90% of the values, the middle 90%, if you did inverse norm center, right? Those two Z scores for the middle 90% would be 1.645. The two Z scores for the middle 95% are 1.96, and for 98% are 2.326. This is how I know those things before I actually plug them in my calculator, because I've memorized these over the years, and I expect you to have these memorized. You need to memorize those three values. You don't want to have to go into the tables and find that critical value. So to create a confidence interval, it's your sample proportion plus or minus your margin of error. And the margin of error calculation is your Z star your critical value times the standard error. Standard of error calculation in this chapter is square root of P hat Q hat over N. It doesn't matter what chapter we're in, confidence interval is going to be the same general idea. Your point estimate, meaning your sample proportion, your sample difference, your sample mean, plus or minus margin of error. Your margin of error calculation is going to change a little bit depending on whether we're talking about one proportion or two proportion or means or standard means and standard deviations. One mean, two means, matched pairs. We've got a one proportion Z interval and test. We have a two proportion Z interval and test. That's this unit. Next unit, we have a one sample T test and interval, a two sample T test and interval, and a matched pairs T test and interval. But it's all the same general idea for all the intervals. It's our sample plus or minus the margin of error. What assumptions must be true? Same assumptions as the last chapter. Independence. The individuals or what I'm sampling must be independent, and the sample size needs to be sufficiently large. We've already talked about these conditions. The conditions make sure that it's okay to make those assumptions. It's okay to say it's independent if it's reasonable to say, yeah, okay, each person's opinion is generally independent of each other if the sample's random and less than 10% of the population. So the randomization and 10% condition check the assumption of independence. Your book is going to include a statement in the conditions about independence. It's reasonable to say that each person's opinion about chicken is independent of the other next. But that's only really reasonable to say if it's a random sample, because if you talk to anybody in my family, we're going to choose Chick-fil-A over Cane's. I prefer the sauce. Okay? So my kids think the same way as me, right? They actually think the same way as their dad. Whatever dad says, they follow. If dad doesn't like something, they don't like something. If dad likes something, they like something. It's me. My opinion doesn't matter. So, and then is the sample size large enough? Is your success failure condition the NP and NQ greater than 10? Do you expect at least 10 successes and failures? Now remember, in the real world statistics, you're checking to make sure these conditions are true when you are designing the experiment, when you're designing the survey, so that you can make sure that you can go on and make that confidence interval. So when they do political polls or poll anything in the United States, they poll 1,000 people. Even if it's 1%, they've met their 10 successes and failures, right? Even if the proportion is 1%, they've met their 10 successes and failures for 1,000 people. They make sure it's a random sample. They make sure it's less than 10% of the population. So if I wanted to do a study at Elsinore High School and find an estimate of the proportion of students who are in an AP class, obviously I can find that actual percentage, right? But if I was just asking, I could sample 100 kids, right? Because I believe that more than 1%, more than 10% of our students are in an AP class. So I met my 10% or 10 successes and failures if I think that's the lowest it probably is. So I could do 100. If I think it's a lower percentage, I may need to ask 200, but I can't go above 200 because we only have about 2,000 students. So then I take away that independence in the sampling with replacement, without replacement. So these conditions have to be true so that we can use the normal model and this calculation is reliable. And so we're checking to see if they did it right. If you're actually doing the study, you're making sure that these are true before you do your experiment or your survey. Okay? And it depends on what kind of test you want to do. Like I said, there's all these different tests you can perform, so you've got to make sure you have an idea of what you're going to use to make those comparisons. So we have those same 3 conditions that we had in chapter 18. Like I said, your book is going to have plausible independence written down. I have never seen that required on the AP exam. Therefore, I will not require that on a quiz or test. You check the 3, randomization, 10% success failure. Remember, if it says a random sample, all you have to say is it says it's a random sample. Don't say it's representative when it is actually random. Let's do our first example. A local newspaper polls a random sample of 330 voters, finding 144 who say they will vote yes on the upcoming school budget, create a confidence interval for the actual sentiment of all voters. So my p hat is what? What is my sample proportion? They didn't give me a percentage, did they? They gave me the numbers. What number goes on top? How many people said they were going to vote yes? 144 out of how many? 330. Okay, that's our p hat. Which is 0.424. Okay. Before I do any calculations, I check conditions. It's never going away. The conditions are never going away for the rest of the year. We will check conditions with every problem we do. Unless it says, assume all conditions are met. Then you do a little happy dance, because that's rare. So my first condition is the sample random? Sample is random. It's actually not good enough, and you'll get marked off on the AP exam if you just write random check. I saw it on homework. Laziness. You kind of want to explain. The sample is random. It stated that. And if you just write 330 less than 10%, also not going to get full credit. Because it's less than 10% of what? You have to say of all voters. No, you don't have to say 330 voters is less than 10% of all voters. But you have to say 330 is less than 10% of all something. It's less than all students at Elsinore High School. It's less than all voters. It's less than all adults in the United States who eat chicken. You have to state what is less than 10% of. Okay? And then the last thing is NP and NQ. Now, NP, if I'm given a proportion, 144 over 330, NP is the numerator. I don't have to go and recalculate 330 times 0.42. It's 144. That's how many successes they had. Yep. That's okay. It's greater than or equal to 10. Okay. And NQ greater than or equal to 10. Well, that's 330 minus 144. It's 186. Your NP and NQ should add to your N. I did 330 minus 144. Well, because if I had 144 successes, if I subtract that, that's how many failures. People that said no. Right? So those two numbers should add to my sample size. If I'm given the numerator of the proportion, that's my NP. If it told me 42% of voters are going to vote yes, or said they were going to vote yes, then I would have to do the calculation. Most of the time they don't report with percentages like decimals. They'll say 52%. They'll round it. And it's okay for your NP and NQ to be decimals when you have to do that calculation. So we're going to add on to our little sentence here, since conditions are met. A normal model is appropriate. One of the criteria on the AP exam is to identify your test by name or formula. So we either have to have all the names of the tests memorized or all the formulas memorized. Which one's easier? Trust me, it's the names. Okay, you don't want to have to memorize every single formula and exactly how to write it out. So we just need to be able to say, these are my conditions, this is the test I'm going to use. This chapter, I will use a 1 proportion Z interval. That's the name of the test we're doing this chapter. A 1 proportion Z interval. Because we're just writing a confidence interval. The normal model is called the Z-score, right? So that's why it's a Z interval. We call it the Z-score. So we want to say that. That's like a whole part of the AP exam. Conditions and identifying the name or the formula that you're using, right? So the formula looks like this. P hat plus or minus Z star square root of P hat Q hat over N. So you can either say 1 proportion Z interval or you have to write the formula down. When we start getting into more complicated subtracting 2 proportions, the formulas get cumbersome. Okay? So that's the standard error. It's this, what's my P hat? 0.424. Now, it doesn't say what level of confidence to use. The default is 95%. So the default is 95% confident. Look back at the last slide. What is the critical value, the Z star, for 95% confidence? 1.96. And that's times the square root of 0.424, 0.576 over 330. And then we put it into our calculator. And I'm going to turn on the insert a video for this. Okay. So what does that look like when we're doing it in the calculator? We can do 0.424. Let's do the negative one. Minus first. 1.96. Plus or minus means you got to add it and subtract it. Times the square root. 0.424. 0.576 divided by 330. I can literally put it all in as 1 and then hit enter. And then what I like to do is hit second enter and scroll over to the minus and change it to plus and hit enter. So my interval is 0.371.477.